Potential due to an electric dipole. Here a dipole is shown. This is minus q charge, this is plus q charge, and at a p point P, at a distance r from the middle point of dipole, we have to calculate the potential. This is 2a, distance between two charge. We will use this relation, trigonometric relation. Here it is a triangle ABC. This side is A, this side is B, and this side is C. You know that cos A equal to B square plus C square minus A square by 2BC. This implies 2B into C into cos A equals to B square plus C square minus A square. This implies A square equal to B square plus C square minus 2BC cos A. This relation A square equals to B square plus C square minus 2 into BC into cos A will be used to find R1 and R2 in this figure. Now the potential at P due to positive charge is V plus equal to 1 by 4 pi epsilon naught Q by R1 due to positive charge at potential P and distance is R1, so Q by R1. Now potential at P due to negative charge, this charge is V minus equal to 1 by 4 pi epsilon naught minus Q by R2. Hence total potential, that is potential due to dipole at P, is V equals to V plus V minus equals to 1 by 4 pi epsilon naught Q by R1 plus 1 by 4 pi epsilon naught minus Q by R2 equals to Q by 4 pi epsilon naught into under bracket 1 by R1 minus 1 by R2. This is equation 1. Now from figure, this figure and this figure, first we calculate R1, value of R1. R1 square equal to A square plus R square minus 2AR cos theta equals to R square into under bracket A square by R square plus 1 minus 2A cos theta by R square equivalent to R square into under bracket 1 minus 2A cos theta by R, because when A is very less than R, hence A square by R square is very less than 1. So A square by R square is neglected with respect to A. So R1 equals to R into 1 minus 2A cos theta by R to the power 1 by 2. This implies 1 by R1 equals to 1 by R into 1 by under bracket 1 minus 2A cos theta by R to the power 1 by 2 equals to, or 1 by R1 equal to 1 by R into 1 minus 2A cos theta by R to the power minus 1 by 2 equivalent to 1 by R into bracket 1 plus 1 by 2 into 2A cos theta by R. Hence 1 by R1 equivalent to 1 by R into under bracket 1 plus A cos theta by R, equation 2. Similarly, we can get 1 by R2 equivalent to 1 by R into in the bracket 1 minus A cos theta by R, equation 3. Using 2 and 3 in 1, we have V equal to 1 by 4 pi epsilon naught under bracket 1 by R into 1 plus A cos theta by R minus 1 by R 1 minus A cos theta by R equals to Q by 4 pi epsilon naught 1 plus A cos theta by R minus 1 plus A cos theta by R. 1 will cancel out. Hence equals to Q by 4 pi epsilon naught R into 2A cos theta by R equals to 1 by 4 pi epsilon naught into 2QA cos theta by R square, or equals to 1 by 4 pi epsilon naught P cos theta by R square. Now since P dot R cap equal to mode of P mode of R into cos theta equals to P into 1 into cos theta P cos theta, hence V equals to 1 by 4 pi epsilon naught P vector dot R cap by R square equals to 1 by 4 pi epsilon naught P dot R vector P vector dot R vector by R cube, then R is very greater than A. At the axis of dipole, theta equal to 0 degree or 180 degree, when theta equal to 0 degree, hence V equal to 1 by 4 pi epsilon naught P cos 0 by R, 1 by 4 pi epsilon naught P by R square from this relation. And when theta equal to 180 degree, V equal to 1 by 4 pi epsilon naught P cos 180 by R square equals to minus 1 by 4 pi epsilon naught P by R square. Potential due to a system of charge. First, a discrete distribution. A discrete distribution of charge is shown, different charge, and this point is P. We have to find the potential at P. So potential at P will be sum of potential due to all charge and given by V equal to V1 plus V2 plus V3 plus that here equal to 1 by 4 pi epsilon naught Q by R1 P plus 1 by 4 by epsilon naught Q2 by R2 P plus dash 1 by 4 pi epsilon naught Q1 by R1 P equals to sigma I equals to 1 to n 1 by 4 pi epsilon naught Qi by Rip equals to 1 by 4 pi epsilon naught sigma I equals to 1 to n Qi by Rip. B. Continuous distribution of charge. For linear distribution of charge, here it is shown. The elemental length is dl and we have to find the potential at point P which is distance r, at distance r. So dv equal to 1 by 4 pi epsilon naught dq by r equals to 1 by 4 pi epsilon naught lambda dl by r. Hence v equals to integration dv equals to integration 1 by 4 by epsilon naught lambda dl by r. Similarly, v equals to integration 1 by 4 pi epsilon naught sigma ds by r for surface charge distribution and v equals to 1 by v equals to integration 1 by 4 pi epsilon naught rho dv by r for volume charge distribution. Here sigma is surface charge density and rho is the volume charge density. Now equipotential surface. It is a surface with a constant value of potential at all points on the surface. Concentric sphere, this is concentric sphere, this is concentric cylinder. For surface 1, in this case surface 1, VA equal to VB equal to VC equal to V1, and for surface 2, VP equal to VQ equal to VR equal to V2. Here V1 is greater than V2, that is potential at 1 is greater than potential on surface 1 is greater than potential on surface 2. In this case VP equals to VQ equal to VR equal to Vs, and again VA equal to VB equal to VC equal to V3. Here it is sold. This surface is of 20 volts, so at all point A, B, C will have same potential. In this case S, R, P, Q all have same potential, and in this case M, N, L have same potential. E equal to BB equal to 20 volt, BS, BR, BP, BQ equal to 30 volt in this case. The electric field is normal to the equipotential surface and its direction is from higher potential to lower potential. Here it is shown. The work done in moving a charge from one point to another point on an equipotential surface is 0. The delta W A to B equals to Q into delta V A to B equals to Q into VA minus VB equals to Q into VA minus VA equals to 0. Since VB equal to VA, which is this is a equipotential surface, the magnitude of electric field is given by E equal to delta V by delta R, where delta V potential difference between any two surfaces and delta R perpendicular distance between the surfaces. Here E equal to dV by delta R equal to delta V by AC 20 minus 10 by 0.1. Ten by 0.1 equal to 100 by Newton per Coulomb. Here figure, in this figure it is shown AB equal to 20 cm and AC equal to AB cos 60 equal to 20 into cm into 1 by 2 equal to 10 cm equal to 0.1 meter. Next, relation between electric field and potential. Consider two equipotential surface with potential V and V plus delta V as shown in figure. The perpendicular distance of surface A from point P is delta L. Let a unit positive charge is moved along this perpendicular from the surface P to surface A against the electric field. The work done is this process is mod of E into delta L, which is equal to the potential difference VA minus VB. Thus, mod of E into delta L equals to VA minus VB equals to V minus V plus delta V. This implies mod of E into delta L equals to minus delta V, that is mod of E equals to minus delta V by delta L. Since delta V is negative, this implies mod of E equal to mod of delta V by delta L. Another method, V equal to 1 by 4 pi epsilon naught Q by R, differentiated with respect to R, dV by dr equal to Q by 4 pi epsilon naught d by dr 1 by R equals to Q by 4 pi epsilon naught d by dr R to the power minus 1 equals to Q by 4 pi epsilon naught into minus 1 into R to the power minus 2 minus Q by 4 pi epsilon naught into R to the power minus 2, or dV by dr equals to minus Q1 by 4 pi epsilon naught into Q by R square equals to minus E. Hence E equals to minus dV by dr. Vector form dV equals to E vector minus V vector dot dr, or integration of dV equals to minus of integration E vector dot dr vector. Electric field is in the direction in which the potential decreases steepest. Its magnitude is given by the change in magnitude of potential per unit displacement normal to the equipotential surfaces at the point.